Hi, I'm Owen, and today we're going to be talking about, as you can tell from the title, the trials and tribulations of NISQ, or Noisy Intermediate Scale Quantum Computing. For those of you familiar with this channel, this is a little bit different than the usual coding and or paper reviews that I often do, but I wanted to sort of summarize a few of my thoughts on the current state of quantum computing and where I see things going in the future. So, just to give a sort of outline, what this is going to be about is basically just me talking about what I think we're at with NISQ, what succeeded and what failed with NISQ, and what the future is going to look like. I want to say right off the bat that these are my personal opinions, and just to make sure that no one takes this the wrong way and I don't get in trouble at all, this is in no way financial advice. We're not going to be talking a lot about finance. It will come up a bit at the end, but I just want to be clear about that. I don't think anyone could confuse this with financial advice, but there's a lot of money involved sometimes with quantum computing. So I just want to be upfront about that. Now, getting into it, I'll just highlight basically a sort of thesis that I'm going to be presenting here. I'm going to be taking a somewhat perhaps more contrarian perspective than I truly personally hold. But that's just sort of just to go against the grain, basically, of the zeitgeist. So the thesis, I'll just read it out now. We're on the precipice, if not currently out of, the NISQ era of quantum computing. NISQ has been largely disappointing, and I think in terms of what a lot of people had hopes for, I think it has failed. And meaningful quantum advantage has not been achieved. For those of you saying, hey, wait, what about this XY experiment? We'll get to that later, I promise. With the next phase of quantum computing upon us, and you'll see why I think it's the next phase, we need to rethink what NISQ is and define what this next era is going to look like, and create productive understandings, dialogues, and realistic goalposts for the next, 3 to 8 years, realistically. And that's really what I'm going to be talking about today. You might disagree with me, and that's fine. I welcome disagreement. I sort of often take a skeptic stance, and I love to be shown wrong and shown. I often take a skeptic stance, especially, for example, with machine learning, and I love it when things work. That's always cool. And so, if you're, and I'll say this at the end too, if you're saying, hey, wait, no, there's really meaningful things that are happening now or could happen in the next year, tell me about it, because I am open to changing my mind. I just sort of wanted to present this in such a way to sort of work against what a lot of people are saying. So let's get into it. This is for people pretty familiar with quantum computing is the target audience here. If you have no familiarity, you might be a little lost, but I'm not going to be getting super technical at all. So you don't need to be up to date on any sort of papers or anything like that. But a basic level of quantum computing understanding would be beneficial for this presentation. So what is NISQ, first of all, when I'm talking about this? I already said it's noisy intermediate scale quantum devices. These are really the two things that I'm going to be sort of using to define NISQ. We have quantum computing, the NISQ era and beyond, and that was the foundational sort of text that introduced, I believe, even the terminology of NISQ by the famous John Preskill, and that was in early 2018. And then just recently there was the complexity of NISQ, which presents a NISQ as a complexity class with certain parameters. And so both of these papers, of course, everything I talk about will be linked in the description. I'm not going to put any citations like live links in the presentation because you won't be able to click on them. So I'll just put them down below in the description labeled as always. So these papers will be among them. So you can check those out if you want to know more. So what is NISQ? I said literally what NISQ stands for, but what are the characteristics of it? If you look at the complexity of NISQ, you'll notice three important things that they define immediately. And I'm not going to claim to have full understanding of everything when it comes to complexity theory. So, take everything with a grain of salt. But noisy gates, noisy state prep, and noisy measurement at the end of the circuit. Now, you might notice your first reaction, like mine might be, well, wait, that's literally always going to be true. That's true of classical computers. We have noise in classical computers. We don't even, I have never once thought about the noise in a classical computer when I'm programming, but it is there, and you'll notice it if you overclock or if you get a blue screen, you'll definitely notice the noise. It's very low levels though. It's important to sort of put some bounds on what levels of noise we consider, because fault-tolerant quantum computing will never truly be perfect. Nothing in the real world is ever perfect. But the important thing I want to emphasize here is the measurement at the end. I also want to mention that noisy state prep is also a theoretical requirement. There's a very interesting paper I saw that will also be linked, talking about the third law of thermodynamics in quantum computing, which, if we prepare the ground state 000, we can only do that at basically 0 Kelvin. And so we always prepare some thermal mixed state, no matter what, in our quantum computer. It's a very interesting paper. That's sort of a tangent, but I'll link that below. So what are the pragmatic features? A lot of this, I'm pulling the data from the Preskill paper. So he defines NISQ, and that's just what I'm going off of, is his definition basically. And maybe it would also be beneficial, if nothing else, to come out of this video is to have a more formal and up-to-date definition of what NISQ is. So he defines it as 50 to a few hundred qubits, with 50 being a major milestone, 2 qubit error rates that are currently above 0.1%, a maximum of 1,000 2 qubit gates, and a 1% measurement error. And that's approximately, give or take, on some of those numbers on what exactly the thoughts are. And so now I'm going to say, well, where are we now? Okay, well, that's sort of what NISQ is. So what are we now on these different features? The state of the art, some of these are ranges that I sort of just approximated. A few of them are from specific ones. So the quantum volume, and this is what I believe to be the biggest. I may be incorrect though, and if I'm wrong on any of these numbers, feel free to correct me, is 13. And of course I'm using log quantum volume as one should. The true quantum volume of that, the non-log, is 8,192. That's set by Honeywell. Qubits, 433, I believe, is the largest, with IBM, an announcement just recently. 1 qubit median gate errors are about 10 to the minus 5. 2 qubit gate errors are 2.2 to 0.5%. Here again, we're doing the percent conversion, so that's 2 times 10 to the negative 3 and 5 times 10 to the negative 3. Measurement errors are between 0.2 and 0.6%. And the largest circuit I've seen that's a non-error correcting circuit, it's important to note, as is pointed out in the paper. So we're not making a logical qubit, we're trying to get some result out of these circuits, is 3,186. That was in a somewhat recent paper, I guess, entitled, I have it up, Simulating Large Size Quantum Spin Chains on Cloud-Based Superconducting Quantum Computers. Of course, it'll be linked below. I put not 1,728 because there was a claim made by Jay Gambetta at IBM that their 1,728 CNOT gate was the largest circuit. How it sort of gets into semantics of how you define largest, but if you define largest as number of CNOT gates, then that's not the case. Now, it is worth noting that is true if you define largest as number of qubits. That was a 127 qubit circuit that IBM ran, whereas the spin chain circuits were 102 qubits. But largest seems to imply depth times width, and in that case, the spin chain would definitely be larger. So just wanted to, there was a discussion on Reddit about that as well. So I just wanted to, point that out. And dynamic circuits, which means mid-circuit measurements, basically, are available on many hardware providers. IBM just announced it. Google has them. I'm pretty sure Honeywell has them. So the measurements at the end are no longer the case. So the takeaway here, at least my takeaway, is, well, NISQ seems like it's over or almost over, right? If we go back, I'm going back. Let me check just real quick to make sure this is all recording. Yep. Then we have, we have more than a few hundred. 433 is almost 500 qubits. That's more than a few, I think. 2-qubit error rates are not yet at 0.1%, but I imagine we'll be there very soon. We're breaking 1,000 2-qubit gates, and we're less than 1% measurement error. So we are sprinting past these metrics that were set forth for the NISQ complexity class, or for the NISQ class. So NISQ is almost over. That's my takeaway. So what comes next, right? A lot of people say, oh, there's NISQ and there's FTQC, fault tolerant quantum computing. Fault tolerant quantum computing full scale is, I don't know, a little ways away. My guess would be at least 10 years away at a minimum. I don't see it coming much sooner than that. But so what's going on between then? We have a decade, realistically probably more than a decade, between NISQ and our next defined class or era. So it's important to sort of think about what's going to come next, and we'll talk about that more too. Now, what is/was, I'm going to operate under the assumption that NISQ is going to continue for a little while longer. But what is NISQ good for? Well, everything. If you listen to any popular science sort of media, you're going to say, oh, NISQ can solve climate change, NISQ can solve, all of drug discovery, NISQ can solve supply chain planning, NISQ will solve operation management, NISQ will solve MP hard, like NISQ is bigger than fire, stuff like this. And that's per some people with some interesting, monetary investments. As a quick aside, I just want to say that you should always follow the money in claims like these. Even if claims are true, you can make a true statement, but there can be financial incentives as to why that statement is being made as opposed to other statements, or what is being unsaid versus what is being said. This is true even in scientific papers. Now I'm not saying scientific papers are wrong or any given paper is wrong. I'm just saying always think about why someone is saying something. Famous examples: the sugar industry pays off scientists to blame fat. That's still something people don't even accept today, even though it's been well established or is not common knowledge, is that the sugar industry, people often say, oh, cardiovascular disease is all because of fat, not because of sugar. Well, that's, the sugar industry in the 60s paid for this research to happen to blame fat. And of course, I'll link, if you're interested in reading more about that story, of course, it'll be down there. You can see this all the time. If you want to see politicians curiously praising a certain industry, perhaps you should look at what industry gives them lots of money. Investors hype quantum to try and get returns on investments. Here's another example that I just saw recently, and of course I'll link this paper. Microsoft says it'll take hundreds of thousands to millions of qubits to achieve practical quantum advantage. I think that's probably true. To achieve practical fault-tolerant quantum computing, I think advantage can be achieved before then. I jokingly put in a not currently retracted paper because Microsoft notoriously had their foundational hardware paper retracted. And you will say, why is Microsoft saying this? And they don't have any chance of winning near-term hardware races. They're sort of all in on this fault-tolerant case. So this is really important for it to be true for them, because if companies are able to create value in the near term, that's going to be really hurtful for their business model. And so it's also important to note, I'll just expand on the retraction a little bit. I'll link, of course, Retraction Watch, which keeps track of this sort of information. There's been a number of retractions regarding the basis of their topological systems, which are called, and I'm probably going to mispronounce this, Majorana particles, Marjona, I believe is how it's spelled. I'm not sure if that's pronounced correctly, but there was a paper which claimed to find them in certain situations. It got retracted. I want to give a huge shout out. I've never met this person or talked to them, but there's a scientist by the name of Sergei Frolov. Again, sorry if I'm mispronouncing that name, but they have worked tirelessly to ensure the scientific quality of a lot of these papers. I haven't seen someone truly helping the scientific community as much as them in any way, I think. So, you know, I always, whenever I see one of these papers come out, I'm like, well, let's wait and see what he has to say about it. And so I jest, of course. I think this paper is the paper that Microsoft said this in will not get retracted. I'm just saying that, you know, they want this to be true. And you can see this true in startups. Startups say, you know, on the counter side, right, I have Microsoft saying it'll be a long time because they want it to be a long time before value can be created. You have startups saying it won't be a long time because they really need it not to be a long time in order to keep sort of investors interested. And so the key takeaway is just sort of always ask, why is someone saying what they're saying? Now, getting real meta here, you should also be asking, why am I saying what I'm saying? Now, I have no monetary interest in saying any of this. As I said before, this is just my personal thoughts. The real reason I'm saying a lot of this is just for my own benefit, to consolidate a lot of my thoughts, to help the community, and to maybe at the end you'll see help sort of write this down, get papers. I love seeing the little citation numbers go up. So, or you can not believe me and, you know, say this is all part of a big anti-NISQ funding, you know, effort. But that's sort of just something unrelated to all this, but I think is especially important for having a realistic perspective on quantum computing. So let's get back to it. I know that was like a 5-minute aside, so I'm sorry for that. But what is NISQ good for? Well, everything per investors, less than everything per everyone else. You will often see, perhaps even in my own papers, I didn't check, that NISQ has a killer app or a killer application, and that is variational quantum algorithms. That's a common thing. Yeah, it's referenced in the Preskill paper. Optimization, machine learning is referenced there. Quantum simulation and algorithms with strong exponential speedups. These are other sort of ideas which are other applications which might have some potential in NISQ. And once again, I'm operating as so NISQ is going to continue at least for a little bit. However, as I've mentioned before, and I refer you to my paper on, or not my paper, my video on quantum machine learning entitled "What is QML Good For?" I believe, VQAs are not scaling so hot. As I pointed out then, we have 100 qubit systems available. Now we have 400 qubit, although I don't know if it's actually available yet, but we will have 400 qubit available very soon. And nobody seems to be running variational algorithms on them. You'll see papers from 2018 being, oh, we did our 18 qubit simulation. We can't run on hardware to test scaling or anything because we don't have hardware bigger than that. But we definitely have hardware bigger than that now. You can definitely get hardware access, if you're going to pay for it through like Amazon Bracket up to, I always call it bracket, even though it's bracket. I know it's the notation. I always just call it bracket. To like, I think 80 qubits Rigetti has on there. So that's pretty big. That's a lot of qubits. 127 is also a lot, but nobody seems to be running internally or externally to these companies really big variational algorithms and getting success on them. I think 433 qubits is probably enough to achieve, the VQE on a molecule that's very hard to classically simulate. But it's not going to happen because there's so many problems to variational quantum algorithm scaling. On a literal time sense, you do some back of the envelope scaling for parameter shift differentiation, and you say, okay, wait, it's going to take so long just to literally do the operations because it scales linearly with parameters. There's the optimization challenges of barren plateaus, noise-induced barren plateaus, expressibility. There's just so much going on that they aren't scaling. You can't use that excuse anymore, oh, their systems aren't there. Well, they are there. You run them on it, and the noise is too much or it takes too long, stuff like that. And even realistically, even if they were working, nobody could afford to run them on on an open system. If you have higher or internal access, then maybe. But as I said in my review of optimization techniques paper, it's costing on the order of millions of dollars for reasonable sized variational runs on hardware. If you look at the costs on Bracket or IBM Cloud or Google Cloud, which is really just a portal for IonQ, these costs are not feasible really for anyone, even big companies, to do that, even if these algorithms were there. So VQEs are the killer app that doesn't seem to be killing anything. And other algorithms, to the best of my knowledge, once again, if there's so many papers, I cannot keep track of them. If you're here to say, wait, there has been a great, amazing paper, please share that with me. But there's not been a lot of success outside of it. VQAs either with simulation or with, and anything else, to exponential speedups. It's just hasn't been great. So here is a list. This is, of course, in jest, a lighthearted fun, a list of the useful NISQ applications. And it's empty, and that's the joke, of course. That is a little bit in jest, but also from a place of truth. So I'm going to just preemptively, respond. Some people might be saying, but what about X supremacy or Y advantage? There's about 5 papers out now, to the best of my knowledge. There's the Google supremacy experiment. I believe there's 2 teams in China which claimed advantage, one using superconducting, one using photons. Xanadu put out a paper on photons, and I think there was one more that claimed, advantage or supremacy. And the key word here that's doing a lot of leverage in my past one is list of useful NISQ applications. Random circuit sampling and Gaussian boson sampling are not the most useful applications, and as we have seen, do not imply that other applications will be useful. Google has had Sycamore since 2019, and Sycamore has not revolutionized the world. And so if supremacy directly correlated with, advantage in other areas, I think we'd be really, far ahead right now. I also want to say that supremacy, that paper, personally, I think did a lot more harm than it did good. And as it stands today, is not. Maybe, there's an argument to be made about whether or not it was true when it was released. I'm inclined to be skeptical, but it is definitely not true now. You cannot say that supremacy experiment is still true because, and I will link this below, it has been efficiently simulated on a small cluster of GPUs, 60 GPUs, and far less than 10,000 days to a far higher fidelity. And so it is definitely not supremacy, and even debatably an advantage. So, but of course that got far less press than the initial release. So that's sort of why I say I think it might have done more harm than good. But that's sort of, if you're going to bring up those experiments, I'm going to say they're not useful. That's my response, basically. Then there's another question of creation versus computation, or analog versus digital, if you will. This came up with some of Google's recent work saying, what we're doing this stuff on a quantum computer, these operations, we're not using them as computational machines. Consider, for example, the time crystal. They're saying we're creating a phase of matter using a quantum computer, not as a quantum computing device. They're not doing computing. They're using it as a medium for creation. There's been some other, I think, anions, if I'm even saying that right. I don't know this physics stuff. As braiding went on there or something like that. And that's where I saw this discussion originally. And so the question of if I can create a phase of matter that I couldn't create elsewhere on a quantum computer, is that advantage? And I think that's interesting and useful, but I'm not sure that sort of falls under my domain. I think I'm focused more on the sort of computation and less on the pure creation of sort of phases. And I'm open to a discussion about that, though. So moving on, let's talk about how we got here. And I know I've been breezing through a lot of stuff. I don't want to belabor any points. But how did we get to the point where even skeptics like myself have been feeling a little let down? And while it's true there will always be those that overhype, just as there are those that overhype in machine learning or in, the viruses that eat bacteria, I'm blanking, bacteriophages, that's their name, or in mRNA, there's technologies that have a lot of promise, but people will always overhype them. Especially those people who have strong monetary interests. And so how do we get here where even the people that don't have those strong monetary interests, fell a little susceptible, shall I say, to hype? I don't know. That's my simple. That's my simple answer. I present a little picture here of slightly overhyped papers, get into media, which hypes it a little more. I think overall, I have a lot of respect for certain scientific media publications. But it's still, they definitely do overhype it a little more. And then that just, to the public perspective, through common talking, through investors, that just gets massively overhyped. But that's true of every scientific field, is this sort of trajectory. And so I don't know the answer. I want to hear other people's thoughts too, because this is true of every field. This is true of machine learning. This is true of immunology. This is true of everything. And you might be tempted to say, as I was, well, the money. As I said, follow the money. Well, the quantum's getting so much money. It's hyping everything because there's so much money flowing in. But there's not even that much money flowing in relative to these other fields I just mentioned. Machine learning with their $100 million seed rounds, they're getting $1 billion seed valuations. That's higher than like Rigetti and IonQ's IPOs. Pharmaceutical industry is a massive industry. I mean, that's huge. Quantum computing is a drop in the bucket compared to that. And so I'm not sure if it is the money here. Something else I don't know is going on. And maybe I'm overhyping the hype. It's just in my little niche cluster, and it's because I'm in it that I feel it so much. But I'm open to hear why people think we got here. And as an example, I already talked about supremacy, right? That got picked up. We're like, okay, people understand what supremacy is. A lot of people can understand how, this computation can be impactful. People say, oh, we're there. It's impactful. We achieve supremacy. When, at least circa today, that's not true. And when supremacy doesn't even carry over to useful applications. And so that's why I've always sort of been opposed to the term supremacy, mainly because it's quantum supremacy, that is, mainly because it doesn't indicate anything useful. If supremacy on random circuit sampling is our benchmark, I don't care about supremacy. I care about interesting applications, useful scientific applications. And so that's why quantum advantage, I think, is a more useful term. I might talk about that more in another video, though. So what comes next? I think I made the argument that we're on the precipice of the end of NISQ. Not a lot has been done in NISQ. I don't know of really anything that has been done in NISQ that's meaningful that can't be simulated. So sort of true quantum advantage in a meaningful way, where something where we have like an application where, okay, we ran this experiment, and not only can it not be simulated, but it tells us something new about science, or it gives us a solution to a problem that we will now go out and use in the real world. What do we call this era? I do not know. I am not my strong suit is picking this name. I suggest we call it NISQ 2, because if NISQ is so good, why isn't there a NISQ 2? And really because NISQ is a great name. Noisy intermediate scale quantum is still true. That's still what we're at. But we sort of want to refine it, I guess. So maybe you could think of NISQ as the overarching. Maybe there only is NISQ and fault tolerant, and we're just going to define sort of subcategories within them, in which case NISQ 2 comes after NISQ 1. I'm open to other names. Not a very catchy name, I admit it. And what will this look like? NISQ 2, which will be in the next few years. What will this look like? And here I'm going to make some definitely very good super forecaster predictions. I'm actually a world-renowned super forecaster, for those of you who didn't know. So all of these are 100% guaranteed to happen. There's no way none of these don't happen. Of course, that's all sarcasm. In case I realize I'm very monotone when I speak into a microphone, and I want to come out right off the bat, and you're probably wondering, okay, well, what are your priors, or what are your explanations or sources for these predictions? And this sort of summarizes my sources.
Nice argument, Senator. Why don't you back it up with a source?
My source is that I made it the fuck up.
Of course, I'll source the video. That's from a YouTuber named Max Orr. Is where I took that video from. And so that sort of should give you the vibe of where these predictions are coming from. I am not trying to justify them. I am just guessing. I mean, super forecasting, of course. I'm a super forecaster. And so I don't see any reason why the metrics and these numbers won't continue to get smaller / bigger. And my predictions are, for no real reason, I guess, by the end of 2025, we'll have 0.08% medium 2-qubit gate error, 0.01% medium readout error, 10 to the negative 6 median single qubit gate error. We'll have 1,500 qubits without classical interconnects, so either on a single system or with quantum interconnects. And we'll have 20 log quantum volume, which would be over 1 million, sort of the naive quantum volume. And this will be natively, i.e. without error mitigation. What will NISQ 2 be useful for? I predict it will be for physics, condensed matter, quantum, many-body simulations. That is what Feynman originally sort of, hypothesized, created quantum computing for, is, the famous quote, nature isn't classical, damn it, so if you want to simulate it, it better be quantum, or something like that, right? And so that's the heart and the foundation of quantum computing, and I think that will be the early forms of its usefulness. And the reason I suspect that is because I believe that these are going to be the most resilient to noise, in part because they are more similar to analog than something like Shor's algorithm. I do not believe that many VQAs will be used, and the few that are used will be related to these simulations. That is my prediction. I think error mitigation will be necessary for any meaningful results, but will be extremely difficult to work with. And we won't just be able to apply it to everything trivially because of its, of course, poor scaling. I realize there's an apostrophe in its that shouldn't be there. And it will require a ton of problem-specific tuning. Consider zero noise extrapolation. You have to choose what type of gatefolding. You have to choose what type of extrapolation. You have to choose how much folding to do. All sorts of decisions like this are going to be extremely problem-specific and require a huge amount of human labor and experimenting in order to get advantageous results. And that's my prediction. What's the timeline? I'm sort of saying NISQ 2 can start either January 2023 or the first time we break the 0.1% median 2-qubit gate error barrier. I predict it will, or I'm saying it should last probably, so when's the end of NISQ 2? NISQ 2. NISQ 2, I think, will end with the first meaningful claim of quantum advantage. I predict the earliest that will be is the end of 2026. And so, there's some debate here about, well, what's really quantum advantage, NISQ 3, of course, will come after NISQ 2. It will be post NISQ 2 to early fault tolerant, and early fault tolerant is 50 to 100 logical qubits. I don't know what NISQ 3 will look like. That's another, remind me, let me set a reminder for 4 years to make another video. And then early fault tolerant quantum computing will last until the full, FTQC with at least 1,000 logical qubits. So that's sort of, this is all, I'm not just making up numbers to make up numbers. Well, I am, but also this is sort of to gain perspective or to gain more insight on what the field and what the, era will look like. If we know when it's going to end, we can sort of predict more about it and define more about it. And so when it comes to these sorts of things, what is the research going to look like in the next few years? Well, it's going to be focused on achieving this first quantum advantage. And I think that's going to be in these simulations of quantum systems, of molecules, of something like that. So just to contextualize what's happening right now, what's the state globally of NISQ as we're exiting it? Well, for now, one thing, we're in or about to be in a global recession. Year to date, the S&P 500 is down 15%. You can see a selection of quantum companies. IonQ is down 72%, D-Wave 75%, Rigetti 86%. The rest of these quantum computing is a very small part of it, so don't take quantum to be related. I'm just contextualizing what the tech companies are looking like. We see Google down 33%, Microsoft down 26%, Honeywell up 6%, IBM up 9%. Obviously, quantum computing probably has none to a tiny amount of impact on these stock prices, but this is just sort of to give information about where things stand. That's also supposed to be a greater than, not a less than. There was like 1.4 billion in funding for quantum computing last year. So not huge, all things considered. The performance is sort of consolidated at large companies. Honeywell, IBM, Google hold a lot of the records that I mentioned in the state of the art slide, which are all massive multi-billion-dollar corporations. I don't know if that's good or bad for quantum computing. I would like to see more quantum computing be developed at academic centers, but that's neither here nor there. Academic wise, we see huge growth in publishing. You can check out the QIP submission numbers this year if you really want to see it, especially in applications research and VQAs. This is also something I've talked about in my What is QML Good For video. So here's a call to action. I want to formalize this. I originally thought about writing this up as a lot more formal, obviously with less memes and sarcasm. But I thought I might get kind of a, I don't know, negative feedback from parts of the community. So because I'm not up to date on everything. So if you're up to date on things I'm not up to date on, let's write this up. Like I'm 100% serious. Because this, like, if we write this up and it's like, at least, kind of good and kind of justified, it doesn't even have to be a formal paper. Like the NISQ paper is like a typed up talk, right? It'll literally get thousands of citations. So, if you know more about certain areas than I do, just let me know. And I am 100% serious about writing this paper. It's not long. It probably won't take a lot of work, and I think it could be fun. I also asked a lot of questions and made a lot of predictions. These responses to my questions and my predictions are sort of pulled out of thin air. I want people to start thinking, give your own answers to these questions, and reason about them more too. I'm not really given reasons for my responses because I don't want this video to be 3 hours long. And I invite all ye NISQ defenders to come forth and prove me wrong. As I said before, I like being wrong. I sort of always take a skeptical position on things, but I don't like, being a cynic, so to speak. I like it when things work and very cool things happen. And so if there's some amazing thing that NISQ has done that I have missed, point it out. I'll probably say, actually, I didn't miss that, and this is why I don't think it's big, but that's a fruitful discussion in itself. And that's everything. That's the end of my presentation. So I'm going to go back to the beginning just to say, just to re-emphasize my thesis. I think, and hopefully I've shown at least some evidence, this is not, a paper yet, that we're basically out of NISQ. We need to think about what comes next. That's really the takeaway. Isn't, don't listen to me. Don't listen to what I'm saying, but listen to what I'm asking. You don't have to agree or even listen to my answers to the questions, but I think the questions are worth asking. What does the future look like, specifically this next era? And I think people will agree with me that NISQ has not been a huge success, and that NISQ, as is sort of defined currently, is sort of over, or NISQ 1, if you will. And so what comes next? That's my question. What comes next? I gave some answers. I hope you learned something, or at the very least are now thinking of something, thinking differently about it, or thinking of a response to this. So I'll leave it off here, and I'll simply say, I'll ask to you, whoever the hell is viewing this, what comes next for quantum computing?